Today we are going to see I/O hardware, I/O interface, kernel I/O subsystem, and communication with I/O devices and streams. I/O hardware. Incredibly variety of I/O devices available. The common concepts are port, bus, and controller. I/O instructions control devices. So any I/O instructions you give to the devices, hardware, it gets controlled. Devices have addresses used by direct I/O instructions or memory mapped I/O. A typical PC bus structure. So you can have a PC bus. You can see a PCI bus here. So with this PCI bus, so many devices are connected, like monitor, graphics controller, processor, bridge or memory controller. You can have a cache memory, SCSI controller, that is small devices controller with so many disks, or you can even connect to IDE disk controller, expansion of bus interface, and keyboards with serial and parallel ports. So all the devices were connected to the PCI bus. So you can also have a expansion bus, that is a sub bus, if you want to connect some more devices. Device I/O port location. So each device connected to the bus will have a I/O address range. If it is a DMA controller, the I/O address range will be in a hexadecimal value of 00000F. And similarly for other devices also, device like a game controller, timer, parallel port, graphics controller, serial port, diskette drive controller, interrupt controller. So you have so many devices, but only partial devices and its I/O address ranges have been given here. So you will have some more devices which will have different I/O address ranges. Polling, it determines the state of the device. So each device will be in different states, like command ready. That means the device is ready to execute. It could be it could be busy. So it's in the process. So therefore it is showing the state as busy. Error. So some error happened with the devices. That means it will show the state of device as error. So busy wait cycle to wait for IO from device. So as we have seen already, you have execution of process, and you will have waiting for IO queue. So we have seen it already. So it is executed as an alternative, get input and output from other devices. Afterwards, it will do the processing. The CPU does the process, and again, IO burst. So it is called a CPU burst or IO burst. So a cycle is maintained as IO burst and CPU burst. So therefore, the CPU will wait until the IO devices gets executed. And interrupts. What is an interrupt is the CPU interrupt request line triggered by IO device. So whenever the CPU requests input output device to get executed, then the CPU gets stopped its process. It is called as interrupts. So interrupt handler receives the interrupt. So the handler work is to receive the interrupt and does the process of command which is given by the CPU. So you can have a maskable to ignore or delay some interrupts. Sometimes it is not necessary to execute the interrupts, so you can even ignore the interrupts. Interrupt vector is maintained to dispatch interrupt to correct handler. So vector which will have based on priority, and some may be unmaskable interrupt vector. So interrupt mechanism also used for exception. So whenever a program gets any exception, the interrupt mechanism is executed. And interrupt driven IO cycle. So in this diagram, we can see that the CPU CPU is having a device driver initiates IO. So therefore, the IO is initiated in the second step, and in the third step, you can see the input ready, output complete, or error. Anything any state of the IO device which will be shown. So it will generate an interrupt signal based on the state of the device, and afterwards the CPU receives the interrupt signal and transfers the control to the interrupt handler. What the interrupt handler will do is process the data and returns from interrupt. So once it is out of the interrupt, CPU resumes the processing of interrupted task, and again it starts the device driver initiating IO. That is the seventh step. So this is continued until all the process gets its IO cycle and execution completed. So this is the event vector table. Some of the events are given. So event vector table is nothing but a number will be generated for each vector number is generated for each description of the event processor. So it could be a divide error, or it could be a null interrupt, or it could be any exception. So any interrupt happens based on this a vector number is generated. So even the vector number is used to indicate the OS that this particular interrupt has occurred. So direct memory access. So this direct memory access, it's one of the communication of IO devices. So used to avoid programmed IO for large data movement and requires a DMA controller. If you want to have the direct memory access, you need a DMA controller. Bypasses CPU to transfer data directly between IO device and memory. So these are the 6-step process to perform DMA transfer. So the first step is the device driver is told to transfer disk data to buffer at address X. So this is the command given by the device driver. So the device driver tells the disk controller to transfer C bytes from disk to buffer at address X. So this happens as a second step. And your third step is disk controller initiates DMA transfer. And fourth step is disk controller sends each byte to DMA controller. So after DMA controller transfers the bytes to buffer X, increasing memory address and a decreasing C until C equal to 0. So when C equal to 0, DMA interrupts the CPU to signal transfer completion. So afterwards, the CPU will resume its execution process. So these are the 6-step process of the direct memory access. Application IO interface. IO system calls encapsulate device behaviors in generic classes. So you have every IO device associated with a device driver, which hides the differences among IO controllers from the kernel. So the user will not know any difficulties of using the devices, even it is not supported by the controllers. So devices vary in many dimensions. It could be a character stream or a block of data that gets passed, or it will be a sequential or random access, or it will be a shareable or dedicated. Speed of operation, based on speed of operation, the devices vary. Based on the read only or write only, based on that access request, the devices may vary. A kernel IO structure is depicted in this diagrammatic representation. So you can have at the end hardware, so many hardware devices like SCSI devices, keyboard, mouse, PCI bus, floppy disk drives, AT-API devices. And in the above, you have a kernel and you have a software called a kernel IO subsystem. So this kernel IO subsystem is going to connect the kernel to the devices through the device controller. So each device, you can see that SCSA device is having a separate device driver and also a device controller. So the kernel IO subsystem gives the command to the device driver that will be executed by the devices only if the device controller gives the permission to execute. And what are the characteristics of IO devices? So it is based on some differentiation what we have seen already. So data transfer mode. So if you take the data transfer mode in terminals, it is based on character. So the data will be transferred in terminal as character by character, and in disk through block as block by block. What are the access methods? Is the modem. In the modem, sequential access will happen, and in the CD-ROM, random access happens. When you take the aspect of transfer schedule, the tape will have a synchronous variations and the keyboard will have a transfer based on asynchronous. What is a sharing? So when you use the example of tape, if you take the tape, it is dedicated sharing, and if you take keyboard, it is a shareable device. And device speed characteristics, the device speed based on latency, seek time, transfer rate, delay between operations. So IO direction, when you take the aspect of IO direction, CD-ROM will have only the read-only option, and graphics controller will have write-only option, and disk will have read and write option. So what is block and character devices? Block devices include disk drives. Commands include read, write, seek, raw IO or file system access, memory mapped file access possible. So when you go for character devices, they include keyboards, mice, and serial ports. The commands include get and put, and the libraries layered on top allow line editing. Network devices, varying enough from block and character to have own interface. Unix and Windows NT 99-2000 include socket interface, separates the network protocol from network operation, and includes select functionality. Approaches vary widely based on pipes, first in first out inputs, streams, queues, and mailboxes. So each approach will have a different technique. Blocking and non-blocking IO. Blocking, process suspended until IO completed. Easy to use and understand, insufficient for some needs. The non-blocking IO call returns as much as available. User interface, data copy, which is a buffered IO implemented via multi-threading, returns quickly with count of bytes, read or return. Asynchronous process runs while IO executes. It is difficult to use. IO subsystem signals process, then IO completed. The kernel IO subsystem is which will have scheduling and also the buffering. The scheduling is nothing but some IO request ordering via per device queue. And some OSs try the fairness. When you go for buffering, it stores the data in memory while transferring between devices. So whenever we go for the next accessing of the device, the buffering, the data will be taken from the buffering and it is shown to the user. To cope with device speed mismatch, so sometimes buffering will make the user to wait for more hours. So in order to avoid that, the device speed mismatch, the buffering takes place. To cope with device transfer size mismatch, to maintain copy semantics, the buffering is basically used in kernel IO subsystem. And catching the fast memory holding copy of data, always just a copy. And key to performance, spooling, hold output for a device. If device can serve only one request at a time, that is printing, then the concept is called as spooling. Device reservation provides exclusive access to a device. System calls for allocation and deallocation. Watch out for deadlocks when device reservation happens. So consider reading a file from disk for a process. It determines device holding file. Translate name to device representation. Physically read data from disk into buffer. Make data available to requesting process and return control to process. This is how the file gets read from disk for a process. What is a stream? A stream is a full duplex communication channel between a user level process and a device. A stream consists of a head interfaces with the user process, driver end interfaces with the device, zero or more stream modules between them. Each module contains a read queue and a write queue. Message passing is used to communicate between queues. The stream structure is a user process which will have a stream head. The stream head will have both read queue and write queue. So the read queues till the driver end, the read queues follow the same point towards the stream head. So the user can read anything from the device. And if he wants to write anything into the device, the write queue is followed till the driver end, and the device can get returned by the content given by the user process. Thank you, students.